Now that we understand the idea of a probability mass function, we want to talk about the special case of the uniform probability distribution, which is where all of the values that the discrete random variable can take on have equally likely outcomes or an equal probability of occurring. So we looked at before this general form of a probability mass function where we said if we have a discrete random variable, capital X, the form of our probability mass function is written this way, where we say that the probability that the discrete random variable takes on this specific value x1 is given here, and then we say that this probability occurs when the discrete random variable takes on the value x1. And then on the second line here, we give the next possible value that x can have and its associated probability. And we keep adding more and more lines until we run out of values x1, x2, x3, etc., that the random variable capital X can possibly have. So that's our general form. When we have a discrete uniform distribution, this is what happens to that probability mass function. All those probabilities are constant. And so if we say that that constant probability is equal to C, so C can take on any value between 0 and 1, but that constant probability is C for all of the possible values of x sub I, like these x1, x2, x3, x4 values that we can see for this discrete random variable capital X. And then the probability is 0 for any other values. In that context, one of the simplest examples of a discrete uniform distribution is the probability distribution we see for dice rolls when we roll a 6-sided die. So if we were to build that probability mass function, here's what we need to think about. If we roll a 6-sided die one time, we know, of course, that the values we can get back are 1, 2, 3, 4, 5, or 6. So we could go ahead and list those possible values 1, 2, 3, 4, 5, 6, and then we need to find the probability that one of these values occurs. Well, each of these values has a 1 in 6 chance of occurring. We have a 1 in 6 chance of rolling a 1, a 1 in 6 chance of rolling a 2, a 1 in 6 chance of rolling a 3, etc., all the way up to 6. We have 6 equally likely outcomes, and so for any particular outcome, the probability is 1 in 6. So we could write that as 1 in 6, or we could convert it to a decimal. The decimal value is approximately 0.167. So in our probability mass function here, we're saying that the probability of getting a 1 is 0.167, the probability of getting a 2 is 0.167, the probability of getting a 3 is 0.167, etc. And these are all of the possible values, all of the x values for the discrete random variable x. So the probability of anything else is 0. And so we could say otherwise, the probability is 0. And this makes sense as a probability mass function because this is a discrete random variable. We have a countable set of discrete values. There are 6 values the variable can take on, and they are discrete, they're countable. There are no in-between values. We can't measure in between 2 and 3 to get a dice roll of 2.5. These are the only values. So we have a discrete random variable. So we can say that the random variable x is discrete. So that's our first criteria for the probability mass function. The second criteria is that the probability of each of those values is between 0 and 1, and therefore also by definition that none of those values are negative. And we can see that that's the case. This 0.167 value is between 0 and 1, and it's not negative. So this probability associated with each of these outcomes meets that criteria. We can say that all of the p of x sub I values are between 0 and 1, so we meet that criteria. And then these values have to sum to a total of 1. And we have this 0.167 probability 6 times. And 0.167 approximately times 6 is equal to 1. So the probability of all of the values of x is 1, and we meet that criteria as well. Think about this. Another way to write this probability mass function for the discrete uniform distribution is if we broke it out like this, we could say 0.167. So 0.167 for x equals 1. We could say 0.167 for x equals 2, 0.167 for x equals 3, and we could keep going putting each value on its own line. We've just summarized the probability mass function. We've consolidated it by putting everything on one line, but this says the same thing that this does. It's just consolidated into one line instead of 6. But we have our probability mass function. We have it described algebraically this way. Now we can go ahead and graph it, and that looks like this. We have along the horizontal axis here all of the possible equally likely outcomes of our die roll. We can roll anywhere from a 1 to a 6. And then the probability that our discrete random variable takes on any of those specific values of x is p of x here. Our probability for each of those values is 0.167. So if we sketch in this graph, we see here a uniform probability across each of these equally likely outcomes. And that is why we call it a uniform distribution, because the probability distribution is uniform. It stays the same no matter which value we choose for x. We can see that the value is level and constant everywhere along this horizontal axis for all of these different values of x. And that value is c if we're talking about this form here, where that probability p of x stays level or uniform at this constant c. So that's the simple idea behind a uniform distribution. But as this die roll example indicates, we see it all the time in the real world. So it's important for us to understand that when we have uniform probability across the full set of outcomes, the result is this discrete uniform distribution, the uniform distribution of the discrete random variable.